so important to understand the production mechanisms for cosmic rays, because essentially what we see from relativistic jets is radiation from highly non-thermal particles, which are cosmic rays, as we see on Earth. And it's also very interesting to understand the origin of the highest energy cosmic rays, although probably they are not playing much role in their observed radiation, but still their origin is of great interest for us. Let me start from, well, maybe I need some biological introduction to that. For those who are not familiar with the stuff I'm talking about, there is a property of human mind that it ignores whatever is not in the framework it is used to. So it is not in the framework we are used to. But it's very, very easy stuff. It's just out of the framework. So just try to switch your in the right mode. If you can. Well, sometimes it's not possible to do it consciously. So let's start with discussion of processes which limit observation. Well, first of all, we always have some escape of particles, it's clear. And then we have some various processes for particle energy degradation, synchronous radiation, inelastic collisions, inverse quantum losses, photomeson interaction if we have baryons. There are many more of decreasing photons. And usually we ignore these processes since we are interested in acceleration. We ignore all the loss processes. Just because, well, it seems that it's obviously an obstacle to acceleration. So if there are no losses, acceleration is better. It's not really the case. Sometimes, if something doesn't kill you, it makes you stronger. If losses do not kill acceleration, they make it stronger. And this is what I'm talking about. In fact, it turns out that if we have some losses in photons, in photon fields, they essentially enhance acceleration to very, very large degree. And in some cases, this acceleration becomes so efficient that it looks like an explosion. Therefore, some people like Yuri and Boris prefer to call it an instability. I wouldn't call it an instability. It's just a very efficient process of energy transfer if you do it in a proper way and include all the feedback. Then it is not an instability.
But in order to say that, you have to specify how the acceleration itself takes place.
Yeah. I come to that. So the critical question is to answer the question: what is small for relativistic flow? In principle, we have a usual answer that everything is small, which is much smaller than unity. It's not really the case for relativistic flows. Subrelativistic flows, it's always like that. There is no question. For relativistic flows, there are, in principle, depending on what situation you are talking about, there are, in principle, two answers. One is that small is whatever much smaller than unity, and the other is small is something which is smaller than 1 over m squared. And we have a window between the two. So in principle, we have processes which have very, very low probability, but still they are dynamically important because they are about second threshold. And the reason for that, if you imagine some processes which transfers energy from downstream of a relativistic shock, I don't talk about shocks, but you can easily apply it to shear flows. It's not at all a problem, just for being more specific. So if you have a relativistic shock and you manage somehow to extract energy from downstream and put it into upstream, it's more or less obvious that when it comes back to downstream, it enhances by a factor gamma squared, this energy. So extracting a small fraction of energy from downstream and putting in the right way into upstream, you can, in principle, increase the energy in several steps, increase the energy up to very, very high levels. And this is basically how the mechanism I'm talking about works. But maybe it's instructive to compare it to a typical situation. when we have a normal diffusive shock acceleration on a relativistic shock. And well, there are many papers devoted to the subject. It turns out that unlike subrelativistic shocks where the exact solution is known and it's more or less consistent with what we see, for relativistic shocks it's not the case. We have never seen a relativistic shock. There are some indirect indications for that, but it has never been observed. This is first. And the second, it turns out that the results in spectrum of observed particles at the relativistic shock strongly depends on what you assume about the geometry of non-negative lines. If you assume something easier to calculate, like Keshet and Waxman, they are calculated the spectrum in the case, or you have stochastic random small angle scattering, and the spectrum turns out to be a power law with index slightly different, slightly softer than what is produced by non-relativistic shock. This one. But if you try to incorporate some realistic, so to say, field line geometry, nobody knows what is realistic in fact. If you try to incorporate this, it turns out that you do not produce a power law. You produce a high bump of thermal particles, but not really a power law. Okay, anyway, acceleration in a standard version of diffusive shock acceleration goes like that. You have a particle escaping from the shock into upstream. First, if the particle has a very large load factor, at first it goes faster than the shock itself. But the velocity difference is very small. The shock goes with the speed of light minus c over gamma shock squared. The particle goes with the speed of light minus c over gamma particle squared. Now, the velocity difference is small. At the time when the particle is deflected by the external magnetic field to the degree that projection of its velocity on the shock normal is less than the shock velocity itself, by this time the particle is moving more or less at an angle 2 over gamma, and this gives you an energy increase in each cycle for shock crossing, an energy increase by a factor of 2. This energy increase is deflection angle times Lorentz factor squared. Suppose, I will explain how you can do it. Suppose that you can do some magic and turn out electric charge of a particle. At some point, in the downstream, the particle becomes neutral, so it crosses the shock, goes into upstream, and is not deflected by magnetic field. So it goes faster and faster. It goes with the same speed, but the distance between the particle and the shock increases with time linearly, increases with time, and can in principle be as large as you want, can be larger than the gyro radius of this particle in the upstream medium. And then at some point you do, second time you do the magic, you turn on the charge of the particle and start to gyrate in the external medium, in the upstream, until the shock encounters once again. But by this time, the particles are completely isotropized, and the energy gain will be gamma squared. This is a big difference from standard diffusive shock acceleration.
Why are the particles isotropized? Why are the particles isotropized? Simply because they spend more time there?
Yeah, because you have a time, they have time which was acquired during the neutral stage. This time is essentially proportional to the distance between the particle and the shock. So the larger the distance, the more time they have to isotropize. But you cannot make this distance large for charged particle because at the same time it gets isotropized and deflects and increases with its projection of its velocity. But for a neutral particle you can do it.
Yes, the relevant question would be what's the characteristic time for isotropy, for a particle to get isotropized?
Yes, it's just, of course it's a question of numbers. You just get the magnetic field in the upstream, whatever you have there.
What's huge?
If the number radius is just true for charged particles, but there's no charge.
Yeah, but here somehow make charge exchange here.
It's got to be charged.
After they
After it's no before. After it's crossed the shock.
Like the person time?
long time after it cost the shock. Then it change.
Oh, well, why?
For typical field, magnetic field.
Yeah, well, you want to take
But we'll
some magnetic field like
shock
for
first.
2 microgauss.
And then
We-
it
we
Like
neutral.
you
and then
have
it
in
neutralizes?
interstellar medium.
Let's him
Light should be like that.
answer.
You have particles, you have streaming particles which increase the magnetic field. You have instability which increases the magnetic field. It's not like you have frozen in external magnetic field which gets enhanced by a factor of gamma and shock. It's not like that. The magnetic field increases already in the upstream by these streaming particles by the current. It gets enhanced more or less up to having energy density equal to the energy density of the particles at this place. It's a rapid process. Well, it's similar to instability which is proposed by Tony Bell. You just do it in a resistor regime or for a resistor. But it's a fast instability.
Yeah, but it was shown to saturate much quicker than discussed by Baron Luczek, right?
In what sense, much quicker?
So on the level of unperturbed magnetic field, you do create this short state turbulence, but never exceeding the this underlying magnetic field.
Oh, why?
Because there was a paper also by Anatoly and Nimitz et al. When they built a particle size simulation of
You
this.
get a factor of 10. You don't get a factor of 100.
Of 100, but there are some possible saturations that can even saturate to the lower level. Right?
Factor of 10.
Wow. Well, it's a question, but at least we know the example of supersonic shocks and supernova, and we know for sure that the magnetic field is easily enhanced. It's not just gets shock compressed and that's it.
In what region?
Like that.
In what region?
The supernova shocks.
No, in the upstream or?
Upstream. Well, you cannot get
No.
field amplification in the downstream.
I can.
How?
Well,
If it's a subarachnoid shock, how?
in the Newtonian case, it depends on what you call downstream, but there is a convective instability, at least at the early phases, which people claimed in the old time that this convective instability, especially Rayleigh-Taylor version, drives, it's quickly saturated by Kelvin-Helmholtz and it drives turbulence. So it's a possibility. Now, late times, it's not clear what happens. And,
For a cystic shock, you cannot do it.
well, I'm going to give it a but it's an open issue, I agree.
But as far as I know from calculations, and people doing calculations can perhaps say more about that, as far as I know, it's not a problem to build up magnetic field in the upstream, but it is a problem to keep it from decaying in the downstream.
Is it really important what now for the topic of this talk? What is the magnetic field in the upstream to turn this particle around?
Yeah, because it was said that if you have in the upstream, if you have magnetic field like
Zero.
microgauss,
Yeah.
it's just you cannot isotropize even mildly energetic particles.
Okay. If you put electron there, you do isotropize, right?
Depends on the energy. You can isotropize even protons, depends on the energy. Then it just limits your energy.
But at least the problem is similar to the usual acceleration scenario, right? So,
Not really. This is the same problem.
exactly, that's what I'm saying. It's a problem for both, but it's the same
Yes,
problem
yes,
for
yes,
both.
yes.
No.
Should have done something with the settings. No?
Yoni, we don't really know that protons are accelerated. You only have evidence for electron acceleration, so we have to be careful with...
Well, we do have evidence for proton acceleration. We see cosmic rays.
Wow.
This is an absolute and direct evidence for proton acceleration.
we don't...
Well, we don't know the source of that acceleration, that's for sure. But
I
we
agree.
know that it happens somehow.
It's really fun.
Well, in fact, if you believe some test results on supernova remnants, probably the TV emission which is observed from supernova remnants is from proton-proton pion production.
No, then you should read the papers by Waxman and Katz.
It's very difficult to fit with inverse law. Very difficult. It's possible, still possible with the current result, but very difficult. It's more easier to do it. Proton. Well, okay, then how you can do the magic? One way to do the magic on protons is to have photopion reactions. Normally it's a loss process. You ignore it. You try to minimize it, but don't overshoot. If you minimize it to the right level, so that protons have a chance to undergo photopion interaction, but this chance is not much larger than, it's not close to unity. But this chance is, suppose that it's much smaller. So some protons, not all, some of them, undergo photopion interaction. And in half cases, you have neutrons in the outgoing channel, plus positively charged pion, of course. And this positively charged pion is basically the main source of losses here. It decays into neutrinos and positron. Neutrinos go out, positron remains in the system and can be accelerated further, it can radiate or whatever. The positron energy remains in the system, but neutrinos carry out some energy. Depending on in what regime you have this photopion interaction, like as the people fill out in their high energy tail, the inelasticity can be from 20% up to 50% more or less. Suppose in the worst case you have lost half of the energy in this process. So this is the way you can turn protons into neutrons, and well, for the purpose of interaction, you can assume that proton has lost its charge, decreasing somewhat its energy. Then the neutron, if it has sufficiently low energy, it can just decay in a normal way. If it has large energy and therefore the decay time in the left frame becomes very large, then you can also employ some interactions with photons, photopion production of neutrons, which has essentially the same cross-section and can transform neutrons into protons. You can also have proton-proton interaction with the same result. Some of the protons in elastic collision will be converted into neutrons, and then again in inelastic collision some neutrons can be converted into protons, if you have sufficiently large baronic density to allow for this inelastic collisions. Well, for this cycle, the proton cycle, it requires the presence of dense photon field or dense matter, dense baronic matter. It's essential requirement. But if you consider the limit for the speed limit of the shock for the process to start, it's not that high, because well, if you lose half of the energy in each cycle, basically you need to increase your energy 2 times at the shock, so you need a loss factor of 2. That's enough. Then in each cycle you lose half of the energy, but then you gain gamma squared, which is about a factor of 4. You increase the net increase in energy is about a factor of 2, and you continue the process. If gamma squared is very, very large, like in gamma reversal and lasers, so it operates very, very easy. Then, of course, you have, inevitably, you have some neutrino emission which accompanies the process, the neutrino emission from decaying pions. Well, and just like here, I will later, maybe later come to the electron cycle. If the proton cycle is efficient, then it quenches the electron cycle, which right now. For electrons, you might have a process like this. You have an energetic electron or positron. It upscatters some low energy photon. You have, again, this electron or positron, which has lost some energy, and you have high energy photon. If the process happens in the linear region, then basically all the energy comes in one particle, either into photon or the remaining electron. Then, okay, if it comes into electron, you just wait for another interaction. After some interactions, it comes into photon. You lose some energy in this way. Photon has less energy than initial electron. And then, anyway, this photon can interact with background photons, slow energy background photons producing pairs. So you have, back again, you have electrons and positrons. Their number has increased two times. And you also have this particle which hasn't lost all the energy. So you have the net increase in the number of particles. But each of these particles has lost at least half of its energy. I would say that much more than one half, maybe up to 80–90% of its energy. So it's a large energy loss for each particle, but the number of particles has increased. Well, for this cycle to operate, you don't need very large photon densities because the cross-section for photon production is sufficiently large. It's about Thomson cross-section. But you do need a relatively large Lorentz factor because each particle has, in this cycle, loses almost all its energy. Or it decreases its energy 3 times, so you need a Lorentz factor, at least a few, to counteract this energy loss for each individual particle. And then this cycle actually has 2 regimes. One is, I will remind you that the energy, even if you lose energy of individual particles, the overall energy remains in the system. It remains in photons and protons, and if the system is not transparent to photons, the energy remains in the system. You do not lose the energy. You just spread it over larger and larger number of particles. So in principle, if the Lorentz factor is low, it can allow the process to operate in a, so to say, pumped cascade regime. So you do not increase energy of individual particles, but you do increase the overall energy content. And this is the regime Boris will be talking about later, I guess. But in principle, if Lorentz factor is high enough, you have just normal acceleration. You do increase the number of particles, but the energy of individual particles increases even faster. So you just have normal acceleration of particles with some larger number of particles at the end. In the idealized case, if I inject non-energetic particles into the system, then at each collision with the shock, the particles will gain gamma squared times more energy. So I will have a convergence spectrum like a combination of several peaks with an envelope which has an exponent alpha given here, and the exponent is defined by the ratio of energy gain factor and the probability conversion factor. If this ratio is high, you can in principle have alpha larger, smaller than 2. That means non-integrable spectrum. And it looks like an explosion. You transfer all the energy of the system into highest energy accelerated particles. It doesn't look like hydrodynamics anymore. All the energy in the system is in the highest possible energy particles.
What again are the conditions for that? What again are the conditions for that?
The condition essentially is that the conversion probability is larger than 1 gamma squared. If it's smaller than 1 gamma squared, you do not have a very hard spectrum. You still produce the spectrum. It becomes just softer. The smaller is the conversion probability, or the smaller is the Lorentz factor. The softer is the resultant spectrum. In principle, it can become so that it is negligible, but in any way, the process do operate even below this limit. Just the efficiency becomes lower. But in the regime where the probability of conversion is larger than 1 gamma squared, the efficiency is terrifyingly high, I would say.
So in the standard Fermi acceleration, the factor of gamma squared is achieved only on the first bounce.
Right.
What makes this mechanism different in that gamma squared is repeated again and again and again?
This stage when particle stays neutral makes a difference. When particle stays
kinematics.
Yes, when particle stays neutral, it can go ahead of the shock, basically infinitely.
Right.
Unless you switch on the charge back again, the particle goes ahead of the shock, and the distance between the particle and the shock increases and increases. So then you switch on the charge, and you have some time until the shock comes to the point. This is the distance between the particle and the shock. You still have some distance for the shock to travel. And during this time, the particle can get isotropized. For a charged particle, you do not have this. It becomes deflected immediately after it leaves the shock.
Can I still ask about this just to understand this? So you need isotropization of the particle.
Well, I do not need it. To be exact, I do not need it. It can be that isotropization is not full, just the diffraction angle is larger than 1 over.
Yes,
2
but
over
it's the same that would increase the efficiency of the standard first order Fermi acceleration. Right? If you do have such deflections,
Yes.
then you do have acceleration.
Absolutely.
So, so one condition for this process to operate is firstly you have to have enough like target photons or ambient protons to make the conversion. But the second is one because you don't deflect enough particles, right? So only some, even if you have this conversion, only some part of the protons converted from neutral particles will be deflected enough to be catch up by the shock again, right?
Not really.
Why not?
Almost all of them up to certain energy. But then, as you pass certain energy threshold, the deflection becomes incomplete and less energy.
Yes.
Yes. Eventually, you end up with the largest energy. You end up just you meet the standard shock acceleration at the largest energy. Deflection becomes limited to the factor of 2 over gamma.
Yes, because
And
I just don't understand why then it's more efficient than the standard first order Fermi acceleration, because you have streaming particles and you have even less of protons than usually, because you just convert some only fraction of them, and then you deflect some fraction enough to be catch up by the shock again.
Yes.
So what is different than from the shock, from the standard flows?
I'm trying to explain that. The difference is that in the standard diffusive shock acceleration, you have just normal charged particles. You have downstream, you have something like CO3, or if it's slow magnetized, suppose. Then, if you try to follow one particle, a particular particle which crossed the shock, try to follow its trajectory in a very simplified case. Just for an example, the magnetic field lines are parallel to the shock plane, and we know that intrinsically they are almost parallel to the shock plane. Then what you have is just the particle gets through the shock, it starts to gyrate in the magnetic field, it comes back. But to come back, it has to go 1/2 of the full cycle. 1/2 of the full cycle has the length pi times r. During this time, the flow adverbs the particle to the distance, which is pi divided by 3 times r. You understand what I mean?
Yeah.
So the flow has advected particle to more than 1 gyroradio, so it has no chance to escape.
Yeah.
The only particles which have chance to escape, they rely upon some very, very highly inhomogeneous regions in the magnetic field. So that for some reason you have magnetic field lines which are almost perpendicular to the shock, and across this field lines some particles can escape. This is, well, basically the main problem for the relativistic shock. You have to extract somehow, you have to extract particles from downstream into upstream. And almost all of them are advected in the downstream. If you have a mechanism which easily extracts particles from downstream, you increase the efficiency of the process. And this mechanism is making particles somehow somewhere in the downstream, you make the particle neutral. It doesn't matter how far behind the shock you are. If you make the particle neutral, it can propagate freely. At some point, it crosses the shock and goes into upstream.
I'm going to push on this because you can't have the cake, the stick in both ends. Because on the one hand, you want to use magnetic field generation. I mean, if these particles go to far distances, isotopized, in order to, even if you assume the band mechanism, in order to generate the field, you need anisotropic. You need streaming particles.
Yes.
And these are typically go to distances well beyond in order for it to work, well beyond this typical, streaming distance. So how?
At the time, the neutral particles, when they escape from the shock, they have very, very narrow distribution. They are flying along the
but
shock.
the neutral
normal.
particle don't.
Yes, but then you switch on the charge. At the time you switch on the charge, the distribution is just the same. You have streaming current.
Then you don't have isotropization. It's if the ensemble of particles is isotropic, then it's isotropic.
It's not fully isotropic. You continuously supply more and more particles.
But then the question, if you really have this instability,
Well, why not? It's not isotropic.
because there is a threshold criterion for the instability.
Yeah.
The Bell instability relies on a beam of, I guess, Anatoly can
This
say
is
more.
what you have. This is what you have.
Then I completely
It's a charge beam.
Sorry?
It's a charge beam.
It's a charge beam, and his model, it's the ensemble of particles is quasi-isotropic. That's the idea. Otherwise, you don't gain this. So how do you? It's a different.
But what's the problem? I don't see.
If you don't generate the field, then you can forget about it.
But I mean, you have some field there.
But it's zilch. That's the idea. You need to amplify it by.
I mean, it depends.
Okay,
You're talking
what
about
external
specific
field?
model.
No, but
Is
you
it right?
Right. One by one. Again, look, I will try to explain it. So, suppose you have a particle. So it's just a current element, a single particle is a current element. When the particle is neutral, we have no current. Okay, so it's zero. Then the particle becomes charged.
Yeah.
At the time it becomes charged,
Yeah.
it moves along the shock normal, always. So it becomes charged. You have switched on the current. Then the particle gets isotropized. You decrease the current to zero. Okay, but this gives you current pulse. Each particle coming out of the shock produces a current pulse. You sum up all the current pulses, you have continuous current. This is what you need. So what's the problem?
I didn't follow this. Can talk about it later.
Okay, what is your requirement to external magnetic field?
There is no requirement to the magnetic field as such. If you want to accelerate particle up to some energy, then this energy gives you a requirement on the magnetic field. The higher energy you want to get to, the larger should be the magnetic field. That's it.
Yeah, but I mean this, for example, for GRBs, it's more or less definite conditions and definite requirements and so on.
Well, it looks like in GRBs you are limited. If you accelerate protons, you are limited about 10 to 21 electron volts. For the energy, the magnetic field will be something like 1 Gauss.
External,
One.
too much probably.
0.1 maybe. 0.1 Gauss.
That's what you need. Or
That's,
So
what,
yeah,
that's what you get, assuming the partition between the magnetic field and
so you need amplification by.
Yes, yes,
several
yes.
other
You mean
Definitely.
1 Gauss in order to
Definitely.
keep your proton in the system?
Yeah,
Yeah.
but as Jonathan has said, it's the same for any particle acceleration. You need the magnetic field amplification.
No, because
If you don't
You need a bit
in
more
the-
here than the usual scenario.
It's not because in the Fermi mechanism you have a stream of particles. They are beam. That's why you don't get the energy. In your mechanism, the ensemble is quasi-isotope.
Fine.
The particle, you have a charged beam of cosmic rays.
Yeah, but you need some field to deflect these particles, otherwise they will not come back to the shock.
Yes, but the beam. I'm willing to accept that a charged beam may be able to generate field by
Okay,
this.
if you assume
by
that
this
there is no
mechanism.
problem, if you assume that the magnetic field is not amplified, it is a problem for particle acceleration, but for any mechanism, whatever you take, this is a problem for absolutely, without any exception, it's a problem for any particle acceleration mechanism, if there is no magnetic field. If there is magnetic field amplification, there is no question then. I can't get it.
The idea is it's not just a beam. Basically, you have a cloud of particles hanging around the shock. So they're going back and forth around the shock, right?
Right.
So that doesn't produce a current by itself. Right? What produces a current, because there are as many particles going that way as there are returning. So that's not that current. But at some point, all this cloud is going to move with the shock through the upstream. So that's a current. Right? So you just have this charge moving with the shock on average. So that's what we mean by the current that excites the upstream magnetic field. So similar thing would happen here. You would have this cloud of charge, which will on average move with the shock. So it will produce the same current.
But can I ask then, if you amplify magnetic field by these charges, it happens at the relatively close upstream? Because you don't amplify like in all upstream, right? It's like as long as you have, as the particles are streaming ahead of the shock, right? Charged particles, charged cosmic rays.
Yeah.
So then if you have this little particle that streams much more ahead, basically you don't have amplified magnetic field there because there is no efficient charges that will do this, right? Am I right?
Not necessarily. I mean, the wavelengths in which you amplify depends on the current. And the wavelength also has to be smaller than the Larmor radius of the particle for this non-resonant type of situation.
Yes, so we are talking about a situation that we have a charged particle streaming ahead of the shock, which are not very relativistic, and the question is how to accelerate some tiny fraction of the particles to ultra-relativistic energies by means of this mechanism, right? So you have the magnetic field amplified very close to the shock from the upstream region by the charged particles, which are not that very relativistic, let's say, by Lorentz factor of these particles, few of the order of shock, right? By Lorentz factor, and then, but then you have a neutron streaming much ahead. So what is amplifying magnetic field there?
That's okay.
I don't even,
Yeah, maybe Compton scattering, like a nuclear
I
explosion.
don't even see why you have current.
I do not understand what's the
It's
problem.
neutral
with that.
particles crossing the shock and then
You
get
do not
charged.
have a current, but
You have
as
to
the
show
neutron
that
becomes
this gives
charged,
it's a different
this
setup
moment you
than
switch
the
off
original
the
problem.
Maybe we
If you
can,
have radiated shock, then we have Compton scattering ahead.
let speaker continue, otherwise we will never finish that.
We will finish.
No, by the lunchtime. I think.
Okay, now coming to the estimation of probabilities. Whether they really can be larger than 1 over gamma squared or not.
Hello?
May
Sergey.
I continue? Well, two examples. One is active galactic nuclei, another is gamma ray bursts. So we have typical luminosity or energy release during the event. We have typical distances, we have large photon energies, whatever. We can calculate the optical depth for the photon final production. And it turns out that this optical depth is about a bit less than 0.1 in active galactic nuclei, and just around 10 to minus 4 in gamma ray bursts. In both cases, it seems that gamma squared is large enough to counteract with this small probability of conversion. But then the problem is that to start the whole thing, going, you need the particles protons acquire enough energy to interact with photons inelastically. And that imposes a sort of a lower limit on the energy you can start with. And in active galactic nuclei, it seems that this energy is high enough. It's about 10 to 15 electron volts. But starting from this energy, you can go up to much higher energy. And in gamma ray bursts, it's about 10 to 12 electron volts. And it's not at all a problem to have 10 to 12 particles, because even in the first pass of the shock, if it has Lorentz factor about 30, the particles will, protons will have energy of 10 to 12. So it's not at all a problem. You basically start from thermal particles in gamma ray bursts. In active galactic nuclei, you need some precursor acceleration mechanism which accelerate protons, but nobody has said that standard diffusive shock acceleration doesn't go there. It can be wrong. It produces some spectrum, some distribution of particles, which is rather soft, but then the conductor acceleration takes over. The conductor acceleration produces much harder spectrum, so that essentially all the energy in the accelerated particles can be produced by the conductor mechanism, although it is preceded by some other acceleration mechanism at the beginning at low energies. And the thing I would stop on is that all these estimates are relevant more or less to afterglow stage of gamma ray bursts. In prompt emission phase, if you believe that it is due to internal shocks, that there's no problem for high and photobinary reactions. Instead, you have the opposite problem, how to get photons out of the system, because it's has very large compactness. During the afterglow stage, you still have some high enough conversion of probability, probability of conversion, and then I will say that in principle you have low energy gamma ray burst, you have high energy gamma ray burst. In principle, I can imagine a situation that in a low energy gamma ray burst you do not meet the criterion for efficient work of this converting mechanism, but for large energy gamma ray burst you do meet this criterion almost certainly. And this creates some problem. If this mechanism is at work or not at work, it should make a huge difference in spectra, which is not really seen in gamma ray bursts. Either all of them are somehow operating this conversion mechanism for some reason, I don't know why, or all of them do not operate this mechanism. And this is very, very difficult to explain how you can avoid convergent acceleration if you meet the criterion for sufficient work. Well then, one extra point. The converting mechanism is very different from diffusive shock acceleration in the sense, absolutely talking about, in the sense that you are not limited to critical energy which gives you, which is given by the condition that particle loses all their energy during half of the gyro circle. For low energy particles, they come to the shock, they go downstream, and they have many gyrations before losing their energy, so they radiate almost isotropically in the common frame. In the lab frame, the radiation of course is beamed to the angle 1 over gamma. Then you have these critical energy particles, which lose half of the energy during half of the gyro circle. Standard diffusive shock acceleration stops here. You cannot gain more than twice of the initial energy during one shock crossing. If you lose half of this energy for synchrotron cell radiation, then you are done. You cannot continue acceleration anymore. So it's a critical energy for diffusive shock acceleration. And at this critical energy, the particle distribution in the downstream is somewhat anisotropic. It's just a little bit elongated downwards. So in the common frame, we have more or less isotropic, somewhat elongated beam pattern. In the lab frame, we have 2 over gamma isotropic pattern, more or less. Maybe 1.5 over gamma, something like that. So it doesn't very much different from, doesn't much differ from isotropic case. In the convergent acceleration mechanism, you are not limited to this energy. Suppose we have a particle which is with subcritical energy. It can produce an upscatter proton with the subcritical energy. It goes ahead of the shock in the upstream. Then it acquires gamma squared times more energy in the downstream, and it becomes highly, highly supercritical. So it loses all the energy before being deflected. In the worst case, or in the best case, whatever you like, you produce, in the downstream, you produce a very, very beam radiation, beamed with an angle of 1 over gamma. So in the lab frame, it's almost isotropic. There is, of course, gradual change from highly beamed to almost isotropic emission. As you go to higher and higher energy, the emission becomes more, the beam pattern becomes wider and wider. And that means if you see a fraction of a spherical shock, normally you are limited to fraction which is within a solid angle of 1 over gamma. And in the case of unbeamed radiation, you can see a larger fraction of a spherical shock. That means a larger geometrical delay, and then you can produce some delay in gamma reversing for energy emission. Another situation you can encounter if you look at the jet from the side, so that you do not observe a jet head-on. You do not see normal isotropic radiation from the jet. You just beam to this observer, and this observer sees this normal isotropic radiation which is in red. The side observer do see this radiation, but it is highly, highly redshifted, highly decreased in intensity, so it's almost unobserved. There is a strong observation bias against observing jets from the side. But for this unbeamed emission, specific doesn't apply. You can still see the jet from the side. Even the intensity of this emission somewhat increases if you observe the jet for fast. So in principle, you can have a very, very hard spectrum a jet is observable at very high energies, but it is almost unobservable.
Wouldn't the observed flux decrease dramatically at such viewing angles?
Observed flux decreases, but it
Even if you
decreases.
have a comparable energy spread over a much larger
Yes.
time and a
Yes.
much larger solid
Right.
angle,
Right, but it decreases
your
not,
energy
not
per
as
unit time
fast.
per unit solid angle goes down dramatically.
It decreases not as fast as you would expect. If you have isotropic in the jet frame emission, you would expect to decrease something like 1/theta to the 6. Very, very rapid increase. And here we can have 1/theta squared. It's not that big. You can still have some emission. And one more thought to this is that the larger is the observation angle, the more sources you can observe. So the brightest sources, the nearest ones, are nearer for the case of wide jets than the case of narrow jets. No, there is not such a strong observational bias against this opaque jets. It is there. There is some bias against that, but it's not that strong at all.
You could observe a much larger area if it was there. If it's a narrow jet, you can only observe where you have a jet, like if it's not spherical. So that's another issue.
Can we say it again?
If you had the spherical outflow, this would be more efficient, or half of a sphere.
Oh,
and then
yes.
the thing is,
If the opening angle is much larger than 1 over gamma,
so you do lose a lot
But
of larger energy.
you have M87, or you can apply similar ideas to HNZs where you know that there are jets that don't point at you nearby jets.
well, there are some features to test or to know about this observation mechanism. One very distinctive test is that you cannot observe nuclei by this mechanism. It's absolutely impossible. So if somebody has proved that highest energy cosmic rays are nuclei, it rules out this mechanism definitely. So
By the way, is it
you
not
cannot observe nuclei. You cannot make a nucleus neutron. You can make a single value, you can make it neutron. You can transfer a proton into a neutron, but for nucleus you cannot do it.
You can do this for helium-3, but it is a very tricky business.
What you get? Try
Three neutrons flying in the same direction, then they charge.
But they will be bound or not?
Who knows? But then you will have multiplicity 3.
Yeah.
Might help.
But still, the result will the end result will be protons.
In this context, I think that this is the announced by the Pirogev collaboration that the ultra-energy cosmic rays are much heavier than the protons, right?
Yeah, there are multiple announcements in this.
collaboration.
And I would say that
Not the other experiment, I mean
not-
Pirogev.
Pierre announced also other things, relation with AGMs, and now they wish they to take away now. And so
But
I mean,
correlation
it's
with
not
AGN is based on some analysis on the Terra-Photic catalog, right? This is just analysis of the data.
no.
yes,
It's model dependent analysis. And basically, the difference between different groups, one of them saying that cosmic rays of high energies are primarily protons, and the other saying that they are primarily nuclei. The difference is in different Monte Carlo techniques to calculate the cascades. What they need is to observe primaries at the ground level. They cannot at present. If you do observe primaries at the ground level, you have a very clear distinction because the optical depth for nuclei is larger than for protons.
No, I understand that the reconstruction of the shower depends on the Monte Carlo simulation. I'm just saying that the Pirogev collaboration reported heavier composition.
That only means that their Monte Carlo technique favors heavy nuclei.
Yeah, that's what they can say.
Yeah.
That's what I'm saying.
But there are other groups which are saying just opposite. And at this point, it's a question to the Monte Carlo technique. Which technique is better? I do not know. Maybe the object people have better technique. I do not know. If they do have better technique, then probably we can trust them. If they have, for some reason, if other groups have better techniques, then probably you should trust the other groups. I don't know. I'm not an expert at all in this sense. Okay, so, and then observed particles can reach supercritical energies. I have said about that already, and that means several several conclusions, but one of the conclusions is that you can have synchrotron radiation at frequency higher than you would normally expect. Normally you would expect synchrotron radiation to cut off the energy gamma times mc squared divided by time structure constant. But now you can get to high energies. Then the emergent particle distribution is dependent on the optical depth for photophine interaction, for photon-photon pair production, optical depth. And since the emergent particle distribution is dependent on the source parameter, I would consider this good for explaining very, very much different spectra of various gamma ray bursts and active galaxy. The spectra are different. And this is somewhat in contradiction to what we used to believe in case of diffusive shock acceleration. We used to believe that it produces a universal acceleration spectrum, which is not in agreement with different radiation spectra. And in this case, you have different acceleration spectra depending on the parameters. So you can, in principle, you can fit various spectra in the same mechanism. And two applications for this off-axis emission is that I can, in principle, think of high latitude unidentified gamma ray sources as off-axis blazers, but some of them can be off-axis blazers. And another application is that the prolonged GV emission from gamma ray bursts can be just a geometrical delay of simultaneously emitted high energy photons with broader impact. So to finish with, let's compare diffusive shock acceleration and the conductor acceleration. There are several points, actually 6 points, and these two mechanisms, as you see, they play a draw. This mechanism has 3 points against it, and this also has 3 points against it. Well, what works against diffusive shock acceleration mechanism is clear. The probability of injection of particles in the upstream is dependent on the magnetic field geometry, and in principle it can be very low. It makes efficiency of the whole process for relativistic shocks very low. Then acceleration efficiency itself is dependent on the magnetic field geometry in the sense that as you go to higher energy, in principle you can have a situation that the correlation length of the magnetic field is smaller than the shear radius of the particle in this magnetic field. And then the deflection of the particle will be smaller than you expect in the case of uniform magnetic field. And that makes the limiting energy of acceleration smaller. In the case of converter acceleration, the last step before you get to the highest energy is that you have a particle in the upstream which has energy, the maximum, divided by gamma squared. So you only need that the magnetic field is coherent on this length, but not on the length of the gyro radius of the most energetic particles. So it makes it a bit easier to deflect particles in the case of conductor acceleration. And then, if for some reason you do not have shocks or sharp tangential discontinuities in the flow, then it will be very, very difficult to accelerate particles through diffusive mechanism, because as you smooth out the discontinuity, the efficiency of the process, the acceleration rate decreases very rapidly. Up to some point, at some point, you just have no acceleration at all. In the case of a convergent acceleration mechanism, there is absolutely no problem with injection. You can inject particles from anywhere in the downstream, into the upstream. Acceleration, it's written here, does not depend on magnetic field geometry. It is dependent on the magnetic field geometry, but to a much less extent than in the case of diffusive shock acceleration. And then the convergent acceleration doesn't really require sharp discontinuities. Suppose you have a flow, here the velocity is relativistic, here the velocity is very low, say 0, and there is a gradual boundary between the two. and this boundary is much larger than the gyro radius of typical particles you want to accelerate. In this case, it will be very, very difficult to accelerate particles through diffusive acceleration. But it's very easy to accelerate them for converting mechanism, because if you convert particle here into the neutral state, they go back. So it's easy. Because the change of the velocity in the mean free path of the neutral particle can be much, much larger than in the gyro radius of charged particle.
Are you talking here about the shear layer acceleration? Because then it applies as well for the regular Fermi type. You don't need conversion for this. It was shown, it was discussed that in case of the shear acceleration, when you have relativistic large velocities of the not like tangential discontinuity, the problems with the diffuse shock acceleration don't apply. And there was a series of papers about this. Because every time you are isotropized at both sides of the flow, you gain the factors.
Well, it's not exactly that, and to say even more, there are no sharp discontinuities in nature.
Yes, but I'm saying this, that you have like a shear layer with the velocity gradient. So then, the limitations of the diffuse shock acceleration do not apply for this, for a regular mechanism that is just scattering of charged particles by MHD waves. So you don't have to have conversion mechanism for this situation to apply. And it was pointed in many, many papers that if you have shear layer of relativistic jet, Fermi acceleration is very, very efficient, not limited by the limitation.
Okay, let me put it very, very clear. I'm not against any acceleration mechanism.
Yeah.
What I'm saying is that all acceleration mechanisms work. Then what I'm saying, okay, in the shear layer you have an efficient, relatively efficient acceleration mechanism for particle acceleration without any conversion.
Yeah.
But then, if you do have conversion, it's not just my will.
Yes.
I want to have a conversion. It is there.
Yes, but it will be then
If you have a
always
conversion.
less, because the conversion will always pick up only some particles.
Yeah, but
It will go with more.
in the usual mechanism, you can use only like narrow space, like gyro radius of the particles. The gyro radius is much less than the jet radius. Therefore, you just use just a small fraction of jet power for this mechanism.
Again?
Again,
Let's maybe we can finish it.
Let's finish it.
Let me
Because
just
this is
let me just make it
we can
clear.
do it after
The
and
conversion mechanism
afternoon.
is there. It operates simultaneously with other acceleration mechanisms. What I am saying is that if the conversion probability is high enough, the conversion mechanisms becomes so efficient that it outperforms any other acceleration mechanism. If the conversion probability is high enough. Otherwise, you still have some converter acceleration, but it can be below just normal acceleration, diffusive acceleration. But if the conversion probability is high, the efficiency is so large that it definitely outperforms anything else.
But I just don't understand why it can be higher than a regular scattering. Because then it's like if the efficiency for the conversion is
Yes.
maximum.
You're looking of efficiency in terms of conserving the number of particles involved in the acceleration process. But what you want to have is not the number of particles. What you want to have at the end is the total energy content in the particles. This is the energy of the particles times the number of particles survived. And what I'm saying is that in a regular mechanism, this product decreases, usually decreases as you go to higher and higher energies. But in converter mechanism, it can increase as you go to higher energies. It can decrease, but can increase.
Actually, around the shock, in order to get such a smooth discontinuity, the only reason why you get such smooth transitions in shocks is because of the particle acceleration.
For a shock. Yeah, I'm coming to that. For a shock.
So you can't say that you can't accelerate particles.
Yeah, but look, if you have a shock and you don't have converter acceleration, then it's okay for you. If you have a shock and you do have converter acceleration, it is efficient, then the width of the shock, the width of the transition is defined by the mean free path of neutral particles, which can be much, much larger than the gyro radius of charged particles. And that means you don't have a shock for low energy charged particles. there is no shock for them. It's just a small transition. They do not get heated. Just adiabatically compressed, gaining some energy, that's it. No shock acceleration at all. So it's very selfish. The converter mechanism is very selfish. If it starts to work, it kills anything else.
But still, to work for this, you need a lot of photons. And in quite extended region. And how probable this to happen?
In AGNs we have plenty of those.
Extension of the region is not a free parameter. All you need is the product of the region size times the photon density. This product has to be larger than something.
Yeah, but it is larger than 10 in power 26. Because the cross sections you are working with,
yes,
so 10 to the minus 26.
There are some estimations. And I should point here that in this case, the estimations are done for photon binary reactions, which has smaller cross section than 2 photon per production. That means for electron cycle to operate, it's not at all a problem to have precipitation. The electron cycle can easily operate in any source. I'm just worrying about whether the proton cycle can operate or not.
I'm talking
For
about
electron
exactly
cycle, there is
proton.
no question at all.
Yeah, yeah. I'm talking about protons.
Again, the problem with external magnetic field, to
But,
keep protons around the jet, what is your requirement for this?
As I have said, there is no requirement as such. If you want to go to high energies, you need larger magnetic fields. Then
Yeah, but
you can reverse it. If you have a magnetic field which is of this strength, then you can go up to particle energies. This.
okay, let's take like 10 to 17 centimeters from the black hole.
Boris, maybe we can finish with this.
So,
Because this is just
Yes,
going.
I think everybody has read already
Yeah.
the explanation. Okay, for standard shock acceleration, diffusion shock acceleration, you can start from thermal particles more or less. It's not a problem. For converter mechanism, normally you have to go to some energy high enough to have large probability of conversion as it increases with energy. In some cases, you do not have to go there. As I have said, for gamma ray bursts, you can start converter acceleration right from thermal energies. In some cases, you do have to go up to some energy. There are different kind of acceleration mechanisms. Diffusion shock acceleration clearly doesn't have any requirements on the photon fields, on the density of photons. It can easily operate without any photon at all. But this mechanism do require some really big densities in terms of, say, solar luminosity. It's really big. But in terms of gamma ray burst luminosity, it's okay. And then this mechanism definitely works for subrelativity flows. Under some question, probably it works for relativistic flows as well. Maybe it works for relativistic flows, not so good for non-relativistic, but still. And the converter acceleration usually requires high relativistic flows. It's a drawback if you talk about acceleration in general, but if you talk about particular object like gamma ray bursts and extragalactic nuclei, we know that there are high relativistic outflows. Well, it's not an additional requirement, we just know that relativistic velocities are there. So, in a sense, I would say that for a converter mechanism, maybe it's for gamma ray bursts and for active galactic nuclei, it's not a draw. It clearly wins 2 to 3, more or less. And then one more point to Stockholm is that here, as you analyze these requirements, it seems that all of them are on the side of, on the theoretical side. We do not know about the magnetic field geometry, we do not know about the probability of injection and the shock. But these are theoretical questions. You cannot easily compute it from the first principles. More or less, these are theoretical problems. These problems which are working against the converter acceleration mechanism, they are, so to say, observational. If the source doesn't meet clear observational criteria, if it has luminosity less than required, if it has Lorentz factor less than required, it cannot operate converter mechanism. But all these things against the converter mechanism, they are on observational side. There are no theoretical difficulties with this mechanism. On the theoretical point of view, it's very, very clear and very easy to realize.
What about the lifetime of neutrons? You have a strength, valence, each way will fly away from a shock. And you will have 10 to 15 centimeters from a shock wave in a GFB. It's quite high distance, and after that you should be precise enough to shut back to go to a shock wave.
What you are saying is that for energetic neutrons, the mean free path before they decay is too large for the shock to come after them. That's true, but then you still have these photon fields which can convert neutrons into protons without any difficulty. Just the same quantifying process, the same perception.
Well, about spectra, in the case of GRBs, that might be some problem. That there is some problem because the acceleration is very fast in this case. It's just the energy jumps by gamma square. Then it definitely falls in fast cooling regime. Therefore, we know the spectra. Fast cooling spectra, which is actually not the case. So you can invent some tricks to avoid this, I believe, but it's not.
Yeah.
Anyway, there is this problem, and I
agree.
met this.
Yes, I agree about that. Definitely, that there is a problem with explanation of spectra, but I would say that the problem is somewhat different. That not only that you have fast cooling, you also have cascading. That means
even worse. Just flat.
Yes, that's true. This is a problem, but I would say this is a problem for this is a problem intrinsic to gamma ray bursts, because if you try to figure out what are the limits for the gamma ray burst sources which can avoid internal cascade, it turns out that these gamma ray burst sources have to be inevitably inefficient. Maybe it is the case, I don't know. If they are cascading, we have to invent some way, independently of what is the acceleration mechanism, we have to invent some way to hide this cascade spectrum, or to shape it somehow. Yes, I agree on that, but I was thinking about this fast cooling. It's not really, but in the converter mechanism you can say that the cooling is fast. Because acceleration is also fast.
Yeah.
So it's always across on the time scale of the cooling.
No. You have acceleration by jumps, very long jumps in energy scale, and after this,
this is idealistic picture.
Yeah. To avoid this, you need a slow acceleration, and then balance between cooling and acceleration. Then you have a narrow particle distribution and.
I think you mean fast compared to the dynamical time, not
compared to cooling time.
Cooling time by what process?
By synchrotron of say, or
protons.
No, I mean, we are talking about electrons.
But cooling over the dynamical time.
Yeah, because the electrons are byproduct of this acceleration, and
not necessarily. It depends on the cycle you consider. If you consider
anyway,
cycle, they are byproduct. If you consider electron cycle, just the
but protons also. It will be the main energy source for electrons, because pions decay for electrons, and therefore you will have electromagnetic electromagnetic cascade, which will emit fast cooling spectrum.
Cascade spectrum, not fast cooling.
Or even flat spectrum, even worse, so the acceleration is too much faster than the cooling rate.
Yes, this is what I'm saying. Is that if you switch on the converter mechanism, it is so efficient that it produces a lot of energy, goes into cascading.
That's not a problem for jets, but for agents, but for gamma ray burst.
It's a problem for jets, I guess, as well. You have cascading there. If you want this mechanism to be efficient, it goes into cascading. If you don't want to be efficient, then
it's not necessarily a problem. If your source is homogeneous, you can still produce.
Maybe. It's difficult to answer. I wouldn't say that it kills the mechanism.
Well, if you don't see what it should produce, then how does it produce what we do see?
It doesn't produce what you see for gamma ray bursts, that's the point.
And we don't see what it should